And good morning, everyone. In the next 45 minutes, I will try to convince you that time synchronization is actually critical in power systems, so it will become critical in the future, and we should make sure we actually secure it appropriately. So the work that I'm going to present today is joint work with colleagues at EPFL and with a PhD student of mine at KTH, and it was partly funded by the Success project. Success is a Horizon project on smart grid security that started almost a year ago. But let me start with showing you a map. This is a map of the United States. And the blue dots on the map show PMU locations, so the locations of phasor measurements units in the United States. You see here more than 1,000 dots on the map. So in 2011, when this map was made, there were more than 1,000 PMUs in the US installed. This is 6 years old. I don't have actually similar figures for the European Union. There is no aggregate statistics. I couldn't find it, at least. I know that Norway has a lot of PMU installations, for example. So why do they have so many PMUs installed in the US? PMUs are not cheap to buy and to install, because they can be used for wide area monitoring, protection, and control. They can be used to improve the operational efficiency of the system. You can use it for real-time congestion management, so you can adjust in real time, for example, the level of generation, and to reduce congestion in the network. You can use it for accurately estimating network parameters in real time, even based on frequent measurements. But importantly, you can improve the situational awareness. So you can become aware of a system instability much faster than using traditional measurement technology. So you can get early stability warnings. You can identify and damp frequency oscillations in large interconnected power systems. This is an issue, for example, in Europe, in Norway, you can see oscillations. You can identify separations, inter-area separations. What you see here on the right is the case of the 1996 separation in the US, in the western US, in WAC, when the system basically separated into 4 different areas. You can do anti-islanding protection, and you can do real-time state estimation. So you can estimate the system state, say, 50 times a second. That gives you much more information than traditional technology, which allows you to estimate the state maybe once per minute, twice per minute in the best case. So how do PMUs allow this? PMUs can measure something we call synchrophasors. If you all know what synchrophasors are, you can continue sipping your coffee. Otherwise, I will try to explain you in 1 minute. So what is a synchrophasor? Consider this figure here. This is a very simplified model of a transmission line. We have 2 buses and the line connecting the 2 buses. And we have sinusoidals at the 2 ends of the line that we can measure. So say we measure bus 1 is this figure here, and bus 2 is this figure here. And assume we have a reference cosine. What you see here, I think it's green. This is the reference. You see the same reference here in the other figure. So what you can do now, if the blue curve is the sinusoidal on bus 1, you can measure the phase angle difference compared to the reference in bus 1, and you can measure the phase angle difference on bus 2 compared to the reference. This will be basically the state of your system, this difference to the reference. Now, what do you need in order to be able to do this? You have to have a synchronized reference. That's the key. You must have the same reference at all buses. So you need precise time synchronization. How precise should this time synchronization be? The standard C37 demands accuracy requirements in order to be able to say that the PMU is compliant with this standard. It has to have an accuracy of 1% at most in terms of total vector error. What is the total vector error? This figure shows what it means. Assume that this vector here is the phasor that you should be measuring. So this is the real phasor in the system. what you should be measuring should be within this circle, which has a radius that is 1% of this vector. So you are allowed to have some measurement error in terms of the magnitude of the vector. You're allowed to have some error in terms of the angle of the vector, but together they should not make up for more than 1%. So in terms of amplitude, 1% is of course easy to imagine. It's 1% magnitude error. In terms of angle, it's half a degree. So that's how much you can be off from the actual angle. What does that mean in terms of time accuracy? 1%, assuming that you have a perfect magnitude measurement, you can be 31 microseconds off with your time reference in the PMU. So that's basically how accurately you have to synchronize your clocks in a power system that will maybe span 5,000 kilometers. That's pretty challenging. How can you do that? Well, today, a lot of operators, what they do is they use space-based time synchronization. What is space-based time synchronization? It can be based on GPS. It can be based on GLONASS if you live in Russia. Or it could be based in Galileo in the EU if it became fully operational, or once it will become fully operational. The idea with these space-based systems is that you have multiple satellites. This figure is a little bit blurry, but what you see here is the Earth, if you can see it. You have satellites here. They send signals, and you use trilateration to figure out your location, which you don't need in the case of the PMUs, and the precise time. The accuracy that you can get using space-based synchronization is around 40 nanoseconds. So it's much lower than what you need for PMUs. So it's useful. The alternative is network-based time synchronization. This is being considered in an increasing number of utilities because then you are not dependent on a third-party infrastructure. For example, the US military. How does network-based time synchronization work? The standard that can provide the accuracy required by power systems is IEEE 1588, called PTP version 2, Precise Time Protocol. How does this protocol work? In this protocol, we have a very simple architecture. We have a master. The master has an accurate clock, and the master periodically sends messages to the clients that contain a timestamp. Clients receive the timestamp, and they can set their clock based on the timestamp. Now, does it work this simple? Of course not, because the time it takes for packets to reach different clients can be different. So they would have different clocks. You have to compensate for the time it takes for the packets to reach the clients. How can you compensate for that? Well, you could compensate if you knew the time it takes for a packet to reach a client from the server. Do you know that? No, because for doing that, you actually need precise synchronized time in the client and the server. So what do? What you do is you measure the round-trip time between the client and the server, and then you make a bold assumption that the time is actually symmetrically split between the time from the server to the client and the client to the server. So you usually make an assumption of symmetry or a known level of asymmetry in the propagation and transmission times. So you measure the round-trip time divided by 2, and you say, this is the one-way delay. And this is what I will have to use to compensate the time stamps that are in the messages sent by the server. So this is a very simple principle. Now, what accuracy can we get with these network-based time synchronization? We can get down to 100 nanoseconds. Of course, it depends on what hardware you have. You need hardware timestamping, very good accuracy hardware timestamping. So it's specialized hardware that has a certain cost, of course. Does it work? Yes, there are multiple installations of this. This is widely used in media production, for example. So this is an established technology. Now, given the important applications of phasor measurement units, there is, of course, the natural question, could phasor measurement units be subject to attack? And the answer you should give is, of course, they could be. So we have to make sure that they will withstand the attacks. What you see here is an attack tree for compromising PMU measurements. You probably are used to bigger attack trees. This was pruned because it's spring. So I pruned all the branches from the tree. And I only kept the top ones. So what would you have? How could you compromise PMU measurements? Well, if the PMUs don't authenticate, so don't use any integrity protection for the data they send, you could simply manipulate data that the PMUs send. And that's the simplest one. But of course, if you are a respectful operator, you would authenticate the data that you send from the PMUs. Then an attacker could still launch a man-in-the-middle attack. That would be basically in the setup phase of your communication system. Assume that that cannot be done. What could an attacker do? Well, the attacker could, for example, compromise the PMU. When would they do that? Attacker could hack your system. Remember the Ukrainian blackout? People mentioned that yesterday, as I heard. Alternative, maybe you heard the news, I think it came yesterday, that a security firm found that something like 20% of Android phones are compromised when you open the box. They contain a virus, often in the firmware, if not in the operating system, like BitLocker. So you start to use your phone, and after a while you get a message that now you have to pay $100, otherwise you lose everything that you have on your phone. So they come compromised from the manufacturer. This could just as well happen with a PMU. PMUs are complex systems. An attacker could also tamper with the PMU's transducers. That's a little bit hazardous. You could be electrocuted easily. There is also a fourth avenue for attacks, and that is to manipulate the time reference of PMUs. And there is little thought that had been given to this in the past, and this is what I will talk about. So what could go wrong, or how could an attacker manipulate the time reference of PMUs? Is it possible to do that in a way that remains undetected? So there are 4 questions that I will look at. First, could an attacker compromise PMU time references? Second, if the answer is yes, could such a compromise remain undetected in a system where there is a certain level of detection capability present already? And I will explain you what I mean by detection capability. Then third question is, how easy is such an attack to compute? So is it reasonable that an attacker would be able to do all the computations in real time, for example, for an attack to happen? And then what kind of an impact could an attack have in a system? So let's look at the first question, security of time synchronization. For the case of GPS, you may have heard of recent incidents. This is actually from 2013, when researchers, I think from UT Austin, they hijacked the GPS of a boat, and they managed to send it to the wrong track. So the boat thought that it was going straight, but actually it was turning slowly right, because the attackers spoofed the GPS signal that was sent to the boat. And the idea is very simple. You have a number of satellites in GPS that send their signals. You have an attacker that sends its own spoofing signal to the vehicle. And then what happens? The attacker increases its signal power and slowly overtakes the GPS signals and sends a wrong signal that it can change slowly and diverts the vehicle. So this has been demonstrated in practice. There have been several theoretical and experimental works that showed that it's possible. This is the security aspect. Reliability. Maybe you heard that in 2016, January 2016, GPS was suddenly off by 13 microseconds. And this was due to that they took off a satellite from the GPS system, and the system somehow could not handle this. And actually, it was not the US military that noticed it, but it was people in Finland who noticed that GPS was off compared to their atomic clock suddenly. So they reported it. And then it was fixed after a number of hours. But it shows that reliability is not perfect either in the case of GPS. How about network-based time synchronization? Could you attack that one? If I wanted to be, let's say, sarcastic, I would have left the slide empty when it comes to security for PTP. So what could go wrong with PTP? Well, an attacker could have access to the communication links between the devices in a time synchronization network, or an attacker could compromise one of the elements, switches in the network that is used for time synchronization. What could the attacker do then? Remember that time synchronization depends on estimating the round-trip time between the client and the server. If the attacker manages to compromise, for example, increase the one-way delay between the client and the server, immediately your estimate will be wrong because you relied on the assumption that the round-trip time is twice the one-way delay. But now suddenly it's not. In one direction, the time is much longer than in the other direction. You have asymmetry. So what is actually the status in PTP security? There is an extension called NXK that was done in 2008, but it is actually experimental. And there have been several works that show that it doesn't really work because of the extra computational complexity that it adds to the system. It's not possible using the algorithms that are mandated in this extension, basically HMAC. It's impossible to do the computations in real time as it would be needed in these intermediate switches. The alternative, what people use today, is link layer security, MACSAC. What they do is they authenticate all the packets between the devices that constitute the time synchronization network. So all of these links are basically secure, but there is no end-to-end security. So if an attacker compromises any of the switches, then time synchronization is compromised immediately. And there is ongoing work called security TLV, type length value, TLV, and hopefully this will be standardized soon for PTP. But actually, this standard relies on group keys. So everybody would share the same key. Consequence, if any of the clients is compromised, the entire time synchronization system is compromised. So security is still questionable. You can compromise this by compromising clients. You can compromise the system by introducing a delay, and no authentication will help you against introducing delay. So in summary, PTP is not very secure. You can easily compromise it if you really want to. So the answer to the first question is then yes. An attacker could in principle compromise PMU time references, both for space-based and for network-based time synchronization. So now we come to the second question. Could an attack remain undetected? And to answer this, we have to introduce a system model and a detection algorithm. So let me start with the system model. So consider we have a power system. This is the IEEE 39-bus benchmark power system. It contains 39 buses. That's why it's called a 39-bus system. So you see buses and transmission lines, generators, loads, and so on. You can model this system as a system of 39 buses. So N would be 39. And in each bus, you have a state, which is the complex voltage phasor. Remember the vector? So that's the state in each of the buses. And together, these 39 phasors give you the state of the system. If you know these phasors, you can compute just about anything in this system. Assume that we have a number of PMUs installed. You can see these little boxes. So these would be the PMUs that we install. So we have M PMUs in the system that we installed. And these PMUs can measure voltage phasors. And they can also measure nodal current injection phasors. So basically, the currents that are going to loads or coming from generators. This is our model. So now if we have these measurements, we can define a measurement matrix. This measurement matrix will basically describe what do we measure as a function of the state of the system. Yeah? Remember, the state of the system is voltage phasors, and we can measure voltage phasors and current phasors, right? So the measurement matrix has a very simple structure. For measurements that are voltage phasors, the entry is a 1 because you measure the voltage phasor. For measurements that are currents, you will have the conductance, the complex conductance in the matrix. That's what describes the relationship between voltage and current. Yeah? So now we can have a measurement model which says that whatever we measure is this matrix H times the state of the system plus some random noise, the measurement noise. And this we assume has a certain distribution. Typically, we assume that it's Gaussian for simplicity. So this is our measurement model. Now, problem is, of course, that we have this noise. That's, for this reason, our measurements don't reflect the exact state at any time. So we want to get rid of the noise as good as we can. So what do we do then? We use state estimation. Since we have a linear measurement model, we can use linear state estimation. And that's very fast. So our system state estimate will be x hat. And that can be computed very easily. It's a matrix multiplication. But remember that these are complex matrices. This symbol stands for the complex conjugate. Yeah? So you take the measurements, multiply it by a matrix, and you get your state estimate. To give you an intuition for state estimation, what it means is consider that we have a system where there is one state variable, one real value, x. Yeah? And you have two measurements that you can take, Z1 and Z2. And you know that Z1 is always 2 times x, should be 2 times x, while Z2 should be x directly. Yeah? Now you take measurements in the system, and assume that you measure this Z value. This Z value is not on the line that corresponds to valid measurements, right? If you know that Z1 should always be 2 times x, and Z2 should always be x, then you know that all measurements should be on this line, which has a slope of 0.5. So what you do is then you say, I measured Z, but I know that this cannot really correspond to a real system state. So what I do is I look for the closest on this line, and I say, well, that should be what I should measure. And then I say, and the state corresponding to that is the system state. Yeah? So this is the idea of state estimation. This is how we remove the noise from the measurement, by looking for the closest explainable measurement using the model. So now that you have your system state estimate, you can create your measurement estimate by simply saying, my state estimate is the state that I believe the system has, and I multiply the state by the measurement matrix. Then I get the measurements that I should observe in the state that the system is presumably in now. You have your measurement estimate, and now you can compare the measurement estimate to what you actually measured. So you create the difference of the measurement estimate and what you actually measured. And this is what we will call the measurement residual, denoted by R. If the measurement residual is big, that means that there was a big error in the measurement, and you removed it. Then you use a statistical test for deciding whether, the magnitude of the error that you observed is reasonable, you can accept it, or is unreasonable, it's too big, in which case you will flag the data as bad data, and you will remove it. And you say that there is some error in the data. So this is bad data detection. And this is the detection scheme that we will consider as a detection scheme in the following. This is actually used in practice in real systems. Now, if you look here above, remember we had our system state estimate, x hat, and then we had our measurement estimate, h times x hat. If you substitute x hat here, you see it's h times h transpose h minus 1 h, z. This is z hat. If you subtract z, that will be, basically, you get that the residual is computed as z times this matrix. And we will call this the verification matrix. So F will be the verification matrix. What properties does the verification matrix have? If you have a measurement that is exactly age, the measurement matrix, times a particular system state, so there is no measurement error in your measurements, then if you multiply the verification matrix by the measurement, you get 0. Yeah? So if you have a set of measurements that you manage to take without any error, then the verification matrix would tell you that, basically, that there is no measurement error. Yeah? Is this clear? Yes? OK. So assume that we have such a state estimator and bad data detector for our PMU measurements in the system. Question is, could an attacker create time synchronization attacks that would not be detected by this state estimator and bad data detector? This is the question. In order to be able to answer such a question, we have to define an attacker model. What can the attacker do? What does it know? And so on. So let's define the attack model. Our attacker, we assume, that knows the system model, so the measurement matrix age. And our attacker knows the instantaneous measurements, Z, so the measurements that you, as operator, take in the system at any point in time. You can say that it's a very powerful attacker model. Is that a problem? Well, if our answer is that an attacker cannot perform an attack, even if it has access to all these data, that's good, because then our system is pretty secure, right? If our answer is, well, if the attacker has this information, it can do an attack, then we have to make sure that the attacker either does not get this information, or we have to make sure that we are able to detect the attacks appropriately. So this is what our attacker knows. And then we assume that the attacker can manipulate P time references. So in this figure, I circled 2 PMUs. Assume that the attacker can compromise the time reference of these 2 PMUs. In that case, P would be equal to 2. So the attacker manipulates 2 time references. What does it imply if the attacker manipulates the time reference? It will imply that the attacker introduces some phase angle difference in the measurement that the PMUs take. Remember the phasor? So the phasor will be rotated by a certain value, angle, depending on the time difference that the attacker manages to introduce in the PMU, in the time reference of the PMU. Yeah? So this is the attack model. And throughout, I will assume that each PMU has its own time reference. So when the attacker manipulates a time reference, it will manipulate the time reference of a single PMU with one attack. If it manipulates 2 time references, that will affect 2 different PMUs. So what's the impact of an attack on the measurements? This figure shows that. You have here a measurement, Zm. So this would be the measurement taken by PMU M, a complex phasor. Because of the attack, this angle alpha, this phasor is rotated into the red one, and you have a difference. So this is the measurement error that the attack introduces, this delta Zm. And you can describe delta Zm as you multiply Zm by a complex vector, ui, which is basically the rotation vector, minus 1. So this is the difference that the attacker introduces in the measurements. If the attacker does not attack a measurement, then there is no difference. Yeah? But you still have the original measurement. So question, can the attacker make an undetectable attack now under these assumptions? What would be an undetectable attack? Let's define the notion of undetectability first then. So an undetectable attack would be that the original measurements multiplied by the verification matrix would give you the same result as the manipulated measurements multiplied by the verification matrix. What does that mean? It means that the attack does not increase the residuals that you use for bad data detection. So if you have the original data, not manipulated, you use your bad data detection algorithm and you say, this data is consistent, I accept it. Then after the attack, you would do the same thing. Yeah? So there is no way for you to tell corrupted data from uncorrupted data. So this will be our notion of undetectability. And this is equivalent, of course, to that the difference introduced by the attack, so this delta z, times the verification matrix is equal to 0. So it does not cause any residual, the manipulation itself. If you just look at this equality, it's equivalent to this on the right-hand side. Yeah? Now we can define a matrix. We will call this the attack measurement indicator that will basically tell us which time references are used by which measurements. So say if a certain time reference is used by measurement 1, then in this matrix we will have an entry 1 for that measurement. We don't have to go through this. The important thing is that we managed to show that if you define an attack angle matrix using this matrix, the attack measurement indicator matrix, and the verification matrix, and the measurements, then you can define a condition for undetectability based on this attack angle matrix W, which says that an attack is undetectable if and only if multiplying this attack angle matrix by the rotation vectors -1 is equal to 0. So this is a very simple, compact expression for undetectability. What you have to remember about this is that the attack angle matrix is a function of z. Z is the instantaneous measurements. So to be able to compute this matrix, you need to have the instantaneous measurements. And that's a very strong assumption. Remember that? And the other thing is then, of course, that this u is a rotation vector, right? So it always has a magnitude 1, and you can set the angle of the vector. You can rotate it around. So this is now the condition for undetectability. Now let's see what can an attacker do with this. Assume that an attacker can only compromise one delay. Can an attacker make an undetectable attack? If we have one delay, that means that p is equal to 1. So say the attacker can only compromise the time reference of this PMU. P equals 1. Our phase angles are basically alpha 1. That's the attack that the attacker can introduce. The attack angle matrix is a single complex number. It's one-dimensional, 1 by 1. And the undetectability condition that we formulated on the previous slide at the bottom, remember, using the attack angle matrix, is simply a W, which is a complex number, times a complex number minus 1 is equal to 0. So the attacker has to satisfy this equation with its attack. Question is, can the attacker do that? Well, the attacker can clearly do that if it sets U1 to 1. But what does that mean? The real number 1 has an angle of 0, right? Which means that there is no attack. Yeah? The alternative is that this expression should be equal to 0, but that is almost impossible. It's very unlikely. You would have to set one of the z's to 0. That's basically what you can do. Yeah? So the one on the left will not be 0, so you would have to set this u to 1, which means that you cannot attack the system. So with a single compromised time reference, the attacker cannot make an undetectable attack. And that's good news, I would say. Now, let's get to the bad news. What if the attacker has access to 2 time references? If we have 2 time references, let's say these 2 PMUs, then we have p equals 2, and we have 2 phase angles, alpha 1 and alpha 2. And our attack angle matrix is 2 by 2. So now we have 2 equations. So we have W11 times U1 minus 1 plus W12 times U2 minus 1 equals 0, and a similar equation based on the second row of the W matrix. This is what U1 and U2 have to satisfy. They basically have to solve this system of equations. Yeah? Assume now that the rank of W is equal to 1. So it's not full rank. What do we have then? Well, it's enough then to consider only one of the rows of the matrix because they are linearly dependent, right? So now we have to find a solution to this equation subject to the constraint, remember, that U1 and U2 are complex rotations, so their magnitude is equal to 1. So you have nonlinear constraints. This is under which you have to solve the equations. You can do this numerically, but there is actually a very elegant geometric interpretation of the problem. Look at the left-hand side. The left-hand side is a circle in the complex plane with center minus W11 and radius the magnitude of W11. The right-hand side is again a circle in the complex plane with center W12 and magnitude the absolute value of W12. What do we want to have? We want to find the intersection points of these 2 circles. First question, of course, do these circles intersect at all? They may not. But since we know that U1 equals U2 equals 1 is a solution to this equation, we know that the circles intersect, at least in one point. Then they are tangent. So they may intersect in another point, and that other point will then be an attack. Yeah? So the answer to the question is, if the rank of W is equal to 1, then there is a non-trivial undetectable attack, and this undetectable attack can actually be formulated in closed form and can be computed with 10 or 15 multiplications and additions. So very easily. What if RW equals 2, so the rank of W is equal to 2? In that case, there is no non-trivial undetectable attack. There is no solution to the system of equations. But we can approximate W with a rank 1 matrix. How do we do that? Take W, you decompose W, do an eigen decomposition. W is Hermitian, so you can do this. You will get a diagonal matrix of the eigenvalues of W. What do you do now? You replace the smallest eigenvalue by 0. Then you get this diagonal matrix lambda tilde. It will have a non-zero entry at the top left. That's the biggest eigenvalue. And then you construct an approximate attack angle matrix W tilde. By construction, it has rank 1. So now you can use the previous methodology for computing an approximately undetectable attack. If the eigenvalue that you set to 0 was small, then this attack will introduce a very small residual. So you can still do something, even if rank of W is 2. Now, what if you have more than 2 delays that you can compromise? What can you do then? Let's say that you have 4 PMUs that you can compromise, you as the attacker. And let's say that these are disjoints. So you have these two blue and the two red PMUs that you want to compromise. Now what you can do is actually you can compute undetectable attacks by attacking these PMUs simultaneously or sequentially as you wish. Simultaneously, I mean you take the instantaneous measurements, you compute the attack for both pairs, and you apply it simultaneously. And it will work. It will be undetectable. You can also do it sequentially. You first compute an attack for the red ones. You take the result, and then you compute the attack for the blue ones, and then you apply the final result to the system. It will work. It will be undetectable. What happens if you have overlapping sets of PMUs? So you want to compromise these three PMUs. You know that you can compromise these two because the rank of W corresponding to these two is 1, and the rank of W corresponding to these two is 1. What you can do is you can attack these sequentially. So what you do is you first compute an undetectable attack for the red ones, for example. You take the resulting attacked Z vector, use it as an input for attacking the blue pair, and then you can actually continue. You can go back to the red pair and attack it again, compute a new attack. So you can do this as long as you wish. You will always get new attacks. And this way you can actually compute a countably infinite amount of attacks for more than 2 PMUs. So the number of attacks is infinite, not 1 any longer. Remember, for p equals 2, there was only 1 attack that you could do. For p greater than 2, there's an infinite number of attacks. You can now define a greedy algorithm for maximizing the attack impact. Assume that you want to maximize the misestimation of the power flow on a transmission line. What do? You would, among all the pairs of PMUs that you can attack, you choose the pair of PMUs whose compromise would give you the biggest change of the misestimated power flow. You choose that one. You create the new Z vector. Now again, you find the pair of PMUs that changes the power flow most. You attack that pair, and this way you iterate. So this is a very simple greedy algorithm for maximizing the attack impact. So the answer to our second question was unfortunately yes. We can actually create undetectable timing attacks against PMU time references. The third question is, how easy is an attack to compute? I already told you that it's very simple to compute the actual attack angles. It's a few multiplications and additions. But what about finding pairs of PMUs that can be attacked, so for which the rank of W is equal to 1? That's also part of the problem. Can you do that offline? Or do you have to do that online? Because remember that attackability W depended on Z, right? So how do we find vulnerable attack locations? Remember, we have to find conditions under which the rank of W is equal to 1 for a 2x2 W matrix. So what we are interested in is actually the eigenvalues of W. If one of the eigenvalues of W is 0, then the rank of W is 1, right? So we can compute the index of separation for the W matrix. The index of separation is widely used for expressing the ratio of eigenvalues, so the spread of eigenvalues. It is simply the ratio of the largest eigenvalue and the sum of the eigenvalues of a matrix. For the case of a 2x2 matrix, it's simply lambda 1, 1 divided by lambda 1, 1 and lambda 2, 2, if we take the diagonal matrix of eigenvalues. Now we can give a sufficient condition for the rank of W being equal to 1. We can actually express this index of separation as a function of the determinant and the trace of W, and we can compute it if we know the Z vector. Now, if this index of separation is equal to 1, that means that the smaller eigenvalue is equal to 0, right? Because this ratio can only be 1 if lambda 1, 1 is 1 and lambda 2, 2 is 0. Otherwise, it won't be 1. Problem, this depends on Z. So you have to do this real time. Every time you take measurements, you would have to compute this index. That makes the attack more difficult. Bad news, we can actually provide an offline method for computing attackability by providing a lower bound on this index of separation. And this lower bound basically is only dependent on static values. It's only dependent on the verification matrix and the measurement attack matrix. It's not important how we compute it. What is important is that this can be computed offline in advance if you know the topology of the system, so the measurement matrix age. If you know that, then you can compute this. So if you have this lower bound equal to 1, then of course the index of separation will be equal to 1. That means that the pair of measurements can be attacked. And this only depends on age and the attack location. So we have a very simple tool. Take a pair of measurements, just the location, and you can decide whether they can be attacked independent of what will be the measured values. So the answer is yes, it's very easy actually to find attackable measurements in a system if you have sufficient information. So now the last question, could an attack have significant impact? So we looked at the 39-bus network. We fed it with real load profiles at 50 Hertz. The load profiles were taken from the distribution network of Lausanne. We have 12 zero-injection buses in this system, and we placed 21 PMUs. 13 of these PMUs measure voltage and current phasors, both simultaneously, and 8 measure current phasors only in the system. So this figure here on the right shows you the load profile as a function of time. And you see here, one important feature of this data set is that there is a huge jump in the reactive power at a certain point in time. So there is a transition in the system. It's not at all steady. So first, let's look at basically the residual, the detectability condition. On the top, you see a data set when we performed an undetectable attack. So we took a pair of measurements for this iOS star was equal to 1, which means that they can be attacked independent of the measurement values. And what you see here is that the attack does not change the residuals at all. You see two curves in the figure with attack and no attack, and they overlap. The attack is undetectable. In the figure at the bottom, you see a pair of measurements for which we don't have the undetectability condition. So actually, those cannot be detected. They cannot be attacked in a way that the attack remains undetected. And what this figure actually shows is that indeed, when you perform the attack, that's the dashed line, then your kind of goodness score decreases. So the goodness of the data is lower. I don't want to go into the definition of the p-value. But your data is less good because of the attack. Now let's look at the impact of the estimated power flow for p equals 2. So you have two measurements that the attacker attacks in this case. On the left, you see two buses that we attacked with p equals 2. Remember, there is only one attack that is possible, that is non-trivial. And what you see is that instead of the original power flow, which is the one at 1.5 kilovolt ampere, what you have is 0.5 kilovolt ampere. So it's 1/3 of the original power flow. This is what the operator would see as an effect of the attack. It's a significant impact, significant underestimation of the power flow. On the right, you see a different pair of measurements. And what you see here is that compared to the case of no attack, when you have about 0.5 kilovolt ampere, now suddenly you have 2.5. So you have a factor of 5 difference between the original and the attacked measurements, or estimated power flows. Significant impact of the attack. This is for p equals 2. What happens if you can attack more measurements? So in this case, we have more measurements to attack. What you see is buses, the power flow between buses 16 and 24, so a pair of buses, but now attacking more PMU measurements. At the top, you see the original power flow, and you see 3 curves here. These 3 curves are results of different kinds of attacks. So the first one at the top is when you attack a single pair of measurements. That has a significant impact already. But then when you actually attack multiple measurements, these joint pairs of PMUs, you can increase the attack impact by another 20–30%. And when you use the greedy algorithm and you attack even non-overlapping pairs of PMUs, iteratively, you can increase the attack impact by another 10–20%. You can actually cause an underestimation of the power flow by a factor of almost 10 in this example, which is significant. So even if in reality, this is, say, an overestimation by a factor of 5 of the capability of the attacker, that's significant. So to summarize, the point I wanted to make is that we have to extend this attack tree with these branches here. If an attacker can learn the topology of the grid and knows this measurement matrix age has the PMU locations, it can actually compute the locations of PMUs or identify pairs of PMUs that it can attack undetectably. And it can compute attacks that will be undetectable. Then, depending on the time synchronization technology you use, it can, for example, introduce asymmetric delay if you use PTP, or it could spoof the GPS signal or the Galileo signal, whatever, of the PMUs that it has to, and it can create an undetectable attack that you will not be able to catch with existing technology. The attack could have significant impact and is actually very easy to compute. It takes some effort to implement it, but you have seen Stuxnet, you have seen the Ukrainian hack, so you know that if someone wants to do something, they will do it actually. So the point is, I think, that we have to be prepared for that this could happen. We would need more understanding of the general case for p greater than 2. So is, for example, the set of attacks countably infinite or uncountably infinite? Is it a continuum or a discrete set? But then once we understand that, we need detection algorithms. So how can we detect that the time sources or the time synchronization is compromised in a system? That's one mitigation tool. And the other one is we have to design our system so that it will be more resilient to time synchronization attacks. That time synchronization attacks are more difficult to actually carry out. And with this, I thank you for your attention, and I'm happy to answer questions.